What if I told you that the solid world all around us, the chair you're sitting on, even your own hand, might not be so solid after all? Today, we're diving deep into a truly mind-bending idea from physics, the concept that everything, and I mean everything, can act just like a wave. Okay, so this whole story really kicks off with a mystery that bugged scientists for centuries. It was all about light. Was it a continuous wave, like ripples spreading out in a pond?
Or was it something else entirely? A stream of tiny, separate particles, almost like little bullets of energy. The crazy thing was, the evidence seemed to support both ideas, which, as you can imagine, was just incredibly confusing.
And look, this wasn't just some friendly little disagreement. We're talking about a deep, fundamental crack in the very foundation of physics. You had these brilliant minds lined up on Team Wave and just as many brilliant minds on Team Particle. And nobody, but nobody, could figure out how they could both be right.
And then, just when it seemed like the whole thing couldn't get any more complicated, the story took an even stranger turn. It turns out, this whole question wasn't just about light anymore. Nope. It was about, well, everything.
And that, right there, brings us to the very heart of this mystery. This bizarre but also kind of beautiful idea known as wave-particle duality.
So what exactly is that?
Well, to put it simply, wave-particle duality basically says the universe doesn't like to pick sides. It's not an either-or situation, it's both. Every single fundamental thing, from a photon of light to a tiny electron, has the properties of a particle and a wave at the exact same time.
Now, to really get a feel for how wild this idea was, we gotta hop in a time machine for a second. See, before all this quantum weirdness, the world of physics was, well, it was neat. Almost a little too neat,
Before 1924, the rules seemed super simple. Physicists basically had two boxes they put everything into. In one box, you had matter, stuff with mass, right? Electrons, atoms, you, me. That was all filed under particle. In the other box, you had light, and that was firmly in the wave category. It was a beautifully clean picture, but it was about to get completely smashed to pieces. The first big crack in that neat little picture came from something called the photoelectric effect. This experiment showed that light, when you shine it on metal, can act exactly like a particle. It literally knocks electrons right out of the material. And that discovery just shattered the whole light is only a wave rule.
Okay, so this is where our hero enters the scene. It's 1924, and a young French physicist named Louis de Broglie is looking at this whole mess. And in the middle of all this confusion, he asks this brilliantly simple, almost poetic question.
This question, it was like a thunderclap. He basically thought, hang on a second, if nature lets waves act like particles, why in the world wouldn't it work the other way around? Why couldn't particles act like waves? He had this gut feeling that nature loves symmetry, and that maybe physicists were just missing it.
But here's the thing. De Broglie didn't just ask the question and walk away. Nope, he actually proposed a way to calculate the wavelength of, well, literally any object in the universe, as long as it was on the move.
And this, my friends, became known as the de Broglie Hypothesis. It's this absolutely radical idea that everything that moves, from the smallest electron to the biggest planet, isn't just a particle, it's also a wave. And he backed it all up with this surprisingly simple, really elegant equation. He said that lambda, which is the symbol for wavelength, equals h, which is just a super tiny number called Planck's constant, divided by p, the particle's momentum.
Okay, let's break that down real quick. So, lambda, that's the wavelength we're trying to figure out. H, Planck's constant, is just this incredibly tiny number that's baked into the fabric of our universe. And p is momentum, which is simply an object's mass times its velocity. Now, the really key thing to notice here is where that p is. It's on the bottom of the fraction.
And that little detail leads to a very obvious question, right? If I have a wavelength and a baseball has a wavelength, why don't we see everything around us rippling and waving all the time?
Exactly. I mean, when you throw a baseball, it travels in a nice, clean arc. It doesn't just spread out like a wave in a pond, and the reason why is hiding right back in that equation, specifically in that little p for momentum.
See, it really all boils down to mass. For something big like a baseball, its mass is huge, at least compared to a subatomic particle. And since that mass is on the bottom of the fraction, a huge mass gives you a wavelength that's, well, it's so ridiculously tiny that it's completely impossible to ever measure. But for an electron, which has practically no mass at all, now its wavelength is actually big enough to be noticeable, to have real effects. On that tiny scale, its wave-like nature is everything.
So when de Broglie's idea was finally confirmed, it wasn't just some small step forward for physics. No, it was a massive quantum leap that completely changed how we see reality itself.
And the impact was, well, it was immediate and it was profound. It only took a few years for experiments to prove he was right. Scientists literally fired beams of electrons at a screen and watched them spread out and create interference patterns, exactly what you'd expect from a wave. This wasn't just some neat trick. It became a fundamental cornerstone of quantum mechanics, helping us finally understand why atoms are stable and how the whole subatomic world really works.
So if you take away just one thing from all this, let it be this. The universe, at its most fundamental level, doesn't really care about our neat little boxes. Every particle is also a wave, and what we end up seeing really just depends on how we choose to look at it.
But this whole idea opens up one last fascinating can of worms. If a particle is really this spread-out wave of probability, can we ever actually know with total certainty exactly where it is and where it's going at the same time? Well, that's a mystery for our next explainer.